Alrighty, hello. So we are on day 12. Remember that day 11 this week was our presentation day, so you only have one assignment this week. If you didn't already do a presentation live with me via Zoom, make sure you get one turned in on Flipgrid as soon as possible so that I don't have to mark that late. So today we are learning our final new thing through online learning, and that's going to be the ideal gas law. So looking at your daily tasks, make sure you check that final grade on your project. That should be posted by now. Hopefully I'm on top of grading. Make sure you give me an email if you have any questions. If yours isn't graded quite yet, give me a couple more days, a little more time, and I'll have that graded shortly. Make sure you watch this video, and then you will have some homework tonight, and then you will have a final quiz next week, so make sure you're preparing for that quiz. So, without further ado, let's get started on some notes. So, looking at the ideal gas law, like I said, today you will need just your note sheet that we've been working on and also a calculator. We're going to be integrating moles today into our gas laws. So, one more step on how to finish the gas laws. So, the ideal gas law, what is it? The ideal gas law states it's basically a single equation which is relating pressure, volume, temperature, and number of moles of an ideal gas. So it's relating all three of the things we've already talked about and including moles. So as you recall from last week, in the combined gas law, we looked at pressure, volume, and temperature, and now we're throwing moles into the mix. Everybody's favorite. Then just as a little introduction to the topic, I do have a video from our favorite John Green here.
Gas. It's all around you. It's in space. It's on Mars. It's dissolved in your blood and in your soda. It's everywhere. And it's easy to forget that we're submerged in an ocean of gas, but it's there all the time. You can feel it if you wave your arms around. You can't look cool while you're feeling it, but you can feel it. It's there, those little molecules and atoms bumping around against your hands as you wave them around. Feel it? Are you doing this? I've got good news and bad news about gases. First, the good news, when they're behaving themselves, it is extremely easy to describe their behavior theoretically, experimentally, and mathematically. The bad news is, they almost never behave themselves. The first mathematical description of the behavior of a gas was a link between pressure and volume. In a closed system, like the inside of this balloon, when we decrease the volume of the balloon, the pressure inside goes up. And if we could somehow expand the balloon, then the pressure inside the balloon would go down. If I keep pushing on it, the pressure inside might go so high that it'll break. I can't do it. It's a very strong balloon. The relationship here is a simple one. When you multiply the pressure and the volume together, you get a constant. As long as the temperature and the amount of gas stays the same, so does that constant. It's called Boyle's Law, and it was a pretty big deal back in the 1600s. It's also one of the greatest scientific misattributions of all time. Robert Boyle was a super rich Englishman raised in Ireland. His father was so rich that he paid another family to raise his children. I guess because he was too busy administering lands or something. Boyle had lots of great ideas about science and chemistry. His most important one, and this is arguably even more important than Boyle's Law, being that chemists should publish papers not on what they feel is correct, but rather on theories that have been backed up by experimentation. Richard Townley, a wealthy but considerably less wealthy Englishman, struck up a relationship with Boyle, telling him about some of his work that would disprove one of those but it feels right kind of chemists. Boyle published a paper mentioning that work, which he called Townley's hypothesis, but which ended up, because of Boyle's superior scientific standing and possibly his wealth, being called Boyle's Law. But here's the really messed up thing. The experiments that led to the creation of this theory were actually done largely by Townley's family friend and physician, Henry Power, who was not a member of the aristocracy at all. He was just a working-class scientist. Power was working on a publication that would have snared him the position as discoverer of the relationship between the pressure and volume of a gas, but Boyle, having discussed the ideas with Townley privately, published his first, attributing Townley as the sole researcher, ensuring that Power's contributions were all but lost to history. Henry Power's Wikipedia page didn't even mention Boyle's Law until a few weeks ago, when I personally added a paragraph about it. with proper citations, of course. But no matter who thought it up or who it got named after, Boyle's law is pretty cool. For a given amount of gas at a constant temperature, pressure times volume always equals the same number. But where is that constant coming from, and why is it different for different amounts of gas at different temperatures? Well, it was more than 100 years before we'd figure out the answers to those questions with the help of a Frenchman, Jacques Charles, and our old Italian house elf friend Amedeo Avogadro. Charles and Avogadro created equations much like Boyle's law, with two features of a gas being linked directly together by constants. Charles discovered that volume divided by temperature equals a constant, as long as the pressure remains the same, and then Avogadro figured out that volume divided by the number of moles in the container at a constant pressure and temperature gave yet another constant. But here's the crazy cool thing: all of these scientists were basically dealing with a different form of the same equation, an equation that we must never forget and is going to be stuck in my head until I die. And here's how it works. Pressure times volume is equal to the number of moles of substance times a constant times temperature. PV equals nRT, the ideal gas law, which works for all gases as long as they behave themselves. Now here's the cool part. Using this equation, we can show how all of these chemists were dealing with the same relationship. They were just clumping various variables together in different orders. All of the chemists we just mentioned, Charles, Avogadro, and Boyle, or more properly Townley and Power, figured out their contribution to the ideal gas law experimentally. But more interesting to me is that it can be understood theoretically. First, we have to understand what each of these variables actually mean. In that same way, the atoms and molecules that make up gases are bouncing against things, applying pressure to them. This balloon is inflated because the molecules are bouncing around inside of it, bumping into the inside of the balloon harder than the molecules bouncing off the outside of the balloon. Scientists generally measure pressure with the SI units of force, newtons per area, meters squared, which is shortened to pascals. But since pascals are so tiny, we either use kilopascals or we use the pressure here on Earth at sea level that we call 1 atmosphere or 1 ATM. Completely by chance, 1 atmosphere is equal to 101,325 pascals, but that's so close that we often just say that 1 atmosphere is 100,000 pascals or 100 kilopascals. Volume is the amount of space particles have to exist inside of, so yeah, that makes sense. When the volume goes down, the pressure goes up because there are more particles in a smaller space and they'll each hit the walls more often. N is simply the amount of gas, the number of moles in the system. Here I am decreasing the amount of gas in the system, and in response the volume is decreasing, obviously, but so is the pressure inside the balloon. R in the ideal gas law is called the universal gas constant, even though, as we will see in a coming episode, it is neither universal nor constant. It's 8.3145 liter kilopascal per Kelvin mole. Temperature is experienced by you and me as hot or cold, but at the atomic level it's kinetic energy, literally how fast or slow the average particle is moving. So if temperature goes up, so will the pressure, as the particles are moving faster, and thus will run into the sides of the container more often. So now we know about all of the little bits of the ideal gas law, so let's take a look at it in action. We here at Crash Course generally like to be very safe. This is a little bit overkill here. I put a little bit of water into this soda can, and now I'm boiling it. So instead of atmospheric gas in this can right now, there's water vapor, and it's hot, and all the molecules are zipping around like crazy. We pick it up, and we plop it down inside of that. Oh, and it crushes itself. So what just happened there? Well, let's see what the gas law can tell us. So which of these things are changing? Starting on the right-hand side, R is constant, so that can't change. The temperature of the gas, though, that definitely changed. It drops like mad when it's exposed to the ice water. N is decreasing too, as water vapor is condensing into liquid water. It thus disappears from the gas phase, so the net result on the right-hand side is a decrease, and that means the left-hand side has to have a net decrease too. So on to the left-hand side, the pressure does indeed drop because the lower temperature makes the molecules move more slowly, thus bumping into the sides of the can a lot less than before. And volume drops too, but not quite for the reason you might think. It's really that the pressure inside the can goes so low that the pressure outside the can, the atmospheric pressure, literally crushes the can. Now I understand that you probably don't think this is as cool as I do, but understanding the physical reality of atoms and molecules smacking into things is a special kind of beautiful for me. It's also pretty cool that if you know any 3 things about a gas, you can figure out the 4th using the ideal gas law. Of course, not all gases behave ideally, and all gases deviate from the law at low temperatures or high pressures, but we'll save that discussion for a later episode. Jargon fun time! STP means standard temperature and pressure, which, according to the lords of chemistry, is 0 degrees Celsius and 100,000 pascals, or 100 kilopascals. 1 mole of any ideal gas takes up 22.4 liters of space at STP, which is a fact that can simplify a lot of calculations. Absolute zero is the temperature at which all movement of all particles stops. It is 0 kelvins, or negative 273.15 degrees Celsius. And that's all for this episode. Thank you for watching Crash Course Chemistry. If you were paying attention, you'll...
Alrighty. So, I know that seems like a lot, and it was a lot. It was a lot more information than we generally would go over in class. But on your last homework assignment from Combined Gas Law, a lot of you guys asked, how do we use these in real life? What does this apply to? How do these all interrelate? And that video went into a little bit of that, of how they all interrelate, and then went over the basics of how we got the formula. So, like the video said, the formula for the ideal gas law is PV equals nRT, where the P is, of course, pressure, our V is volume, our N is going to be the amount of moles, so our number of moles is our N. Our R is a constant, which I'll talk about in a second, and T is temperature, and remember this has to be in kelvins. So, our R that we are going to use in this class is our gas constant of 0.0821 liters per ATM. This unit is important. So, depending on what unit you're using for pressure and volume, that changes the R. Notice the R I'm giving you is measured in liters of ATM. So, because we're using liters of ATM for our R, our pressure must be in ATM, and our volume must be in liters. So, you need to remember that this needs to be in ATM. It's going to be really messy. Volume needs to be in liters. Moles will be in moles. Our R is this. And our temperature will be in kelvins. So, you can't use any old unit anymore. You have to use those specific units. So, moving on here, I think we have a practice problem. So, what is the pressure in atmospheres exerted by a 5 mole sample of nitrogen gas in a 10-liter container at 298 Kelvin? So, let's pull up our whiteboard. So, as usual, let's write out what we were given. It tells us that pressure, so it's looking for pressure, what pressure? So our P is our X value. It then tells us is exerted by a 0.5 mole sample, so our N, or our moles, is going to be 0.5 moles of nitrogen gas in a 10-liter container, so our volume equals 10 liters at 298 Kelvin. So our temperature is 298, and that is in Kelvin. So remember our equation is PV equals nRT. So remember our R is always going to be 0.0821 liters of ATM, or ATM times liters. So let's just check our units before we continue. Our P is going to be measured in ATM. We have moles in moles. Our volume is in liters. Perfect. Our temperature is in Kelvin, ATM. Good, so now we are going to plug it in. So we have P, or X, times our volume of 10 is equal to nRT. So is equal to 0.5 times 0.0821 times, oh no, we'll rotate it a little bit, I'll push it out, times our final answer, 298. And then we're going to solve. So first let's multiply all these together. When you multiply those together, you should get 12.233. and that's going to be equal to 10x. Since we're multiplying here, we're going to divide on both sides, divide by 10 to get a final answer of x equals 1.22, and that's going to be an ATM. So that is how you use the ideal gas law. It is, again, just plugging and chugging, plugging in answers and solving, which I know a lot of you said you were really comfortable with in the last assignment. So that is what your homework is basically on for the most part. You're going to have a couple practice problems again like that, and then next week we will be integrating the ideal gas law, combined gas law, Charles, Boyle's, and Guy-Lussac's all into one note sheet, so make sure you're prepared for that. If you're feeling confident, you can go and try out those homework sheets right now. Otherwise, if you want to give it, if you are still feeling a little confused, this next video will go over a little more in depth of how the ideal gas law came to be, go into another practice problem, and it's going to set it up a little bit different. So if you don't quite understand how I solved that, try this problem out and it might make more sense to you.
So here I have a tank filled with gas. And these little dots represent some of the gas particles that would be in this tank. The arrows I put in here because all of these particles are in constant random motion. They're like a bunch of hyperactive little kids running into each other all the time, banging into the sides of the container and so forth. So we've got this tank of gas. Let's think about the characteristics that we could use to describe it, all right? So one of the things that we could do is we could say what its temperature is. The higher the temperature, remember, the faster these gas particles are moving around. So temperature is very important when we talk about gas. Temperature for gases should always be reported in Kelvin. So we could say, for example, that the temperature of this guy here is 313 Kelvin. That's how hot these gas particles in the sample are. When you talk about gas, another important characteristic is pressure, all right? How hard are these gas particles bouncing against the side of the tank? How much pressure are they exerting on them? And we could measure these with, a pressure gauge or something like that on the top of this tank. We could say, the pressure for this is 3.18 ATM, all right? That might be a pressure. And another thing that we spend a lot of time talking about when it comes to gas is volume. And again, I have these letters here that are how each one of these things are abbreviated. Volume V, the volume of this tank might be something like 95.2 liters. And finally, look at these particles that I've drawn, right? There's a certain amount of gas that's in here. And the amount of gas, which is abbreviated by the little letter n, is usually reported in moles, which is a convenient measure of how much of something we have. So we could say that the amount of gas in this tank is, 7.5 moles. Now, whenever we have a sample of gas like this, if it's a tank or it's in a balloon or wherever it is, we can give it these various characteristics. And it turns out that also for any sample of gas, if we know 3 of these characteristics, we can figure out what the 4th is. All we need to do is know 3. And in order to do that, we use an equation that's a representation of the ideal gas law. And it's written as P times V, pressure times volume, equals N, the amount of gas, times R, times T, temperature. I'll get to R in a second. Don't worry about it for right now. It's going to be a number that we know. Okay, so let's say, for example, that we didn't know what pressure was, but we still knew the temperature, volume, and the amount of gas. No big deal. We could take the equation PV equals nRT and rearrange it, divide both sides by V, get rid of the V, and then we'd have P equals nRT divided by V. Plug these values in and we could figure out what the pressure was, okay? Or let's say that we knew what the pressure was of a particular gas sample, we knew what the temperature was and the volume, but we didn't know what the amount of gas was. We didn't know how much we had. We could figure out that 4th characteristic by rearranging the ideal gas law for N, canceling out R and T on one side, rearranging it to solve for N, and then we could plug in the pressure, the volume, and the temperature, and we could figure out the amount of gas. So in other words, if we know 3 of these characteristics, we can always figure out what the fourth is. So you may be asking yourself, okay, so R, what's R? R is what we call a constant. It's a number that we know ahead of time that doesn't depend on the variables in our problem. The R that I'm going to be using most of the time for the videos is 0.0821 liters times ATM divided by Kelvin times mole. Now notice that this is a fraction. It has both a top and a bottom, and it also is not just a number, but it has units. And check this out. The units on R match the units in my problem. They match the characteristics that I'd be using, right? So I have liters here, liters there, ATM, ATM, Kelvin, Kelvin, and moles, moles. You always want the units on R to match the units of the characteristics in your ideal gas problem, okay? So because you always want the units to match, there are also different values of R, although I'm going to be using this mostly for the videos I'm doing. For example, let's say that instead of ATM, I was using a pressure that was in millimeters of mercury. In this case, I wouldn't want to use this R here. I'd want to use this R here so that the units match. Millimeters of mercury here, millimeters of mercury here, and the number is different, 62.4. So again, that's what I'd use here. Let's say that instead of millimeters of mercury, my pressure was given to me in kPa. I would then use this value of R so that the units match. I've got kPa here, and all the others are the same. So 8.31 for that. Now, as I keep saying, in most of the videos that I'm going to be doing, I'm going to be using this top R with ATM. But you may be asked by your teacher to use a different R. It's no big deal. That's probably just because they're giving you problems that have different pressure units and they want...
Alrighty, so that was the wrong video. That wasn't the one I really wanted to show you. My bad. However, he does show how PVR NRT and gets the R value, which is still important. So I apologize. I will post another supplemental video on the link that you can watch if you need extra support. So remember, your homework is right here, your day 12 homework. Make sure you get that in shortly and let me know if you have any questions. Have a good day.